can start it actually.
Sure.
Yeah. So a very good afternoon to everyone present here. I, Dr. Rajkumar Arya, Associate Professor, Department of Chemical Engineering, NIT Jalandhar, the course coordinator. Welcome you all to the second sessions of our fourth day of this online short-term course on computational methods and analysis for engineers conducted by Department of Chemical Engineering. The convener of the course is Dr. Anurag Kumar Tiwari, and patron and head of the department is Dr. Sangeeta Garg. So, a speaker for today, this session is Dr. Gaurav Manik from IIT Roorkee. So, let me introduce Dr. Gaurav Manik to everyone present here. We have amidst us Dr. Gaurav Manik, who is an associate professor at the Department of Polymer and Process Engineering, IIT Roorkee. He holds a PhD from IIT Bombay, MTech from IIT Kanpur, and completed his BTech from SBTI Kanpur in Chemical Engineering. Prior to joining IIT Roorkee, Dr. Gaurav worked with BITS Plani and BIT Jhansi. He is also enriched with industry experience, having worked with 3M, Indo-Gulf Fertilizers and Chemical Limited, Classic Strips Private Limited. Dr. Manik has 106 research publications in international peer-reviewed SCI journals, patent applications, conferences, and book chapters. He has 44 publications in peer-reviewed chemical engineering and polymer science and engineering journals of repute, such as Renewable and Sustainable Energy Reviews, Energy, Composites B, Engineering, Applied Surface Science, Polymers, to name a few, and holds 6 granted patents and patent applications of industrial commercial relevance, contributed to 14 books, and made for 42 conference publications. He has executed 5 research projects and supervised 1 postdoctoral, 2 PhD, 7 PhD ongoings, and 10 master's students and 24 BTech projects. Uh, Dr. Manik has been awarded with the prestigious APAC level Tech Forum Contribution Awards at 3M in year 2012, received Best Innovative Product Award twice in year 2010 and 2011 at 3M, secondment as visiting faculty sanctioned by President of India uh, for the teaching at international platform at Asian Institute of Technology, Thailand, and BICAL Award for best papers by Institute of Chemical Engineers, IICHE, India. He is in the editorial boards of several journals like International Journals of Biological Micromolecules, Applied Energy, Applied Polymer Composites, Composite Science and Technology, Composite B Engineering, Analyst, Biotechnology Reports, Neural Computing and Applications, International Polymer Processing, Journal of Molecular Graphics and Modeling, among others. He is the life member of Material Research Society of India, Indian Society for Technical Education, Academy for Microscope Science and Technology, and American Chemical Society. So with this brief introductions, now I would like Dr. Gaurav Manik to conduct the session. Over to you, sir.
Thank you, Dr. Raj, and appreciate your giving such a detailed description about my professional background. Thank you for the same, and thank you in advance for inviting me on this specific platform wherein you're talking about computational tools for making problems easier for engineers. So I'll start sharing my slides, and uh, the audience can stop me at any point if there's something to be asked, because there are several slides that I would be talking about. and maybe people might forget in the end. So if anyone wants to stop me by in between, they can feel free to do so. I will stop my slides at some point so that there's an adequate time for the audience to ask questions. Um, Dr. Arya, in case my voice, there's an interruption in voice or something, please ping me over phone or otherwise so that we can reconnect back in case there's an issue.
Sure, sure.
Uh, uh, so, Dr. Arya, can people see my slides?
Yeah, yeah, it's come.
Okay, thank you.
Yeah, it's visible now.
Oh, thank you. So this piece of information that I'm going to give is going to be focused on the area of how you can molecularly model materials, how you can computationally solve the problems and estimate their properties. And so, first part of my talk would be majorly focused on giving you a glimpse of the computational tools and the underlying algorithms and strategies which are adopted to solve material problems. In the second part of my talk, I will focus on giving some piece of information about application of these computational tools, which is primarily molecular simulations, in understanding and evolving properties of composites, and polymer coatings. So that's going to be my second part. So first, I'll try as much as possible to make you understand what are these computational tools available that can solve many of the problems. So that's the introduction, and so this is the content part, and we're going to talk about first on the molecular modeling and the computational analysis part. We'll speak about some of the concepts and then some of the general applications. Then we'll switch on to the understanding about taking a case study, how you can solve some of the problems, or how you can understand the structural property relations of materials, how you can evaluate some of the properties of materials like polymer composites. So that's the part that we're going to touch next. And after that, we're going to talk about development of coatings as an example. So the second case study would be focused on coatings. These are primarily I'm going to talk about self-clean coatings, and we talk about some fundamentals of such coatings, and also then we'll switch over how you can use these computational and molecular modeling tools to analyze the coatings, and how they can be useful to assist in the development of coatings. And then finally, we'll summarize and conclude. So this is the general thought about what is molecular modeling. I mean, how does it figure in picture in terms of solving material problems? So the first we're going to talk about the basics of molecular modeling. MD refers to here molecular dynamics, which is a very good computational tool. So we're going to talk about a brief about it. We're going to talk about the intricacies of molecular dynamics in terms of how does it help use the equations of motion, what are the key properties, what are the sample applications, what are the limitations, and what are the software packages which are available that you can use to solve many of the material problems, and then how you can accelerate the molecular dynamic simulations and the concepts of ensemble. So these are general basics about the computational analysis and the molecular modeling understanding. What are the various concepts around it? Uh, the origin of molecular dynamics starts since the year 1950s, primarily 1957, when Alder and Wainwright they came up with the first paper on the phase transition for a hard sphere system. And so the paper on phase transition was primarily focused on using the concepts of molecular dynamics that we're going to discuss in the initial slides. And the whole thought was that can you model an infinite amount of material. For instance, this PET bottle that you have, a small piece of the material might have millions and billions of atoms, but can you represent that small piece of material using a set of kind of simulation cells, which have which is primarily the central simulation cell, but which is kind of repeated by similar cells around it. Okay, so you try to focus on one simulation cells, although in this piece itself there might be 1 billion atoms, but you choose, let's say, about 100 atoms, and with similar surrounded lattices around it. You focus on this central lattice and you try to estimate the properties of this polymer, which could be PET, by only simulating the properties of hundreds of polymers or hundreds of monomers. Okay, so it's that although the whole of this bottle, PET bottle, might have billions and billions and billions of molecules, but how you can model that infinite amount of matter with a very small simulation cell that I've shown on the right. Okay, and how you can use the properties that you estimate from this small simulation cell to estimate the properties of this PET bottle in complete. Okay, so that's the whole thought on molecular dynamics in terms of application perspective. Uh, okay, the sample applications that we have are, for instance, the molecular dynamics can be not only at the level of the water or smaller materials, but you can even use these techniques in simulating the motion of planets and galaxies and stuff like that. The other examples are you can try to understand how do fluids that fall onto any substrate surface, which could be a polymer, which could be a glass, which could be a metal. How do these kind of fluids settle onto these substrates, and how what is the level of interaction of these fluids with the substrate? So these kind of interactions we can kind of between these two entities we can try to understand using molecular dynamics. Okay, and I'm going to show some examples and case studies around it. But that's another interesting application. The other applications could be where you can try to understand how does drug molecules bind with various proteins and tissues in the body, and you can visualize whether the binding of the drug molecules to their receptors will happen or they will not happen. Okay, so some of those case studies we will touch upon. We can also understand the folding and unfolding of protein molecules. So there are several different types of proteins in our body, and with of several different structures. So we can try to understand those structures. We can also try to understand the folding of the proteins into their primary, secondary, and tertiary structure. So we can get a complete whole lot of understanding around that. So what does molecular dynamics in crudely I have already explained to you in the first slide, but let's start
Hello,
talking.
sir. I can't. We can't hear actually.
Is it better now? Hello?
Hello.
Yeah, is it better now? Hello?
Yeah, yeah. Hello.
Yeah, can you hear me?
Yes, sir. Yes, yes.
Okay. Can you see my slides also?
Yes, yes, yes.
Okay, so
All
thank you.
is fine.
So what does molecular dynamics do is what you're trying to do is mimic what atoms will do in the real life. Okay, so materials, like I said, are represented in a small scale by putting individual or connected atoms in a 3D simulation box. So for instance, you could put just a cluster of polyethylene chains into this 3D simulation box. And let's say you can even put some oxygen atoms. Let's say if you want to try to understand the diffusion of oxygen molecules within a polyethylene layer. So you can take, let's say, a few tens or twenties of these polyethylene chains, and then you can put the you can put the oxygen molecules into it, and you can see how the oxygen molecules will diffuse into polyethylene. So this will give you some understanding about the gaseous impermeability of polymers like polyethylene or any of those that you develop. So you have to represent, you have to kind of put such individual or connected atoms in a 3D simulation box, and then you let them interact. So you let the oxygen interact with the polymers and polymers and polymers, and you see how the system evolves. But the whole point is that you would need to know, you can do this only when you know how they are actually going to interact. Okay, so how does one atom interact with the surrounding atoms? You would need to know that before you start doing the molecular simulations or the computational understanding. That can only happen if you know how these molecules interact with each other. So you have to feed in this information to the computer before you start running your simulations. So, two things, couple of things you could do is you can assume a potential energy function, but that will have to be based on some experimental information that you have. And once you have that potential energy function, this will help you to calculate the forces which this atom experiences with several atoms which are surrounding it. Okay. So, given the position of the blue atoms around the red atom, if you know that and you have an understanding of the potential energy function as a function of distance, then you will be able to start moving these atoms based on those forces that they experience. So when we talk about forces, the Newton's laws of forces which affect the motion of atoms will also be employed in this case. The simple Newton law of motion, which is F is equal to ma, the force acting on any body is proportional to the acceleration that it gets. So those simple kind of forces, those so simple kind of equations we employ in molecular dynamics because the central molecule is surrounded by several molecules, and so it will have it will be forced upon by the forces because of the surrounding molecules, and that force will be translated into its acceleration and the velocity. So we use very simple equations, Newton's laws of motion, and we kind of grow or move these molecules based on those Newton's laws and the energy function. So the basic algorithm is that when you start your simulations, you will have to divide, or you will have to have an understanding how much time do I need to simulate. So a time of the order of few milliseconds to 1 second may also be sufficient in some cases to get a lot of the important and interesting properties. But the point is that you have to move your atoms very slowly, and so you can't move them you can't try to understand the motion of the atoms quickly in few microseconds or milliseconds or 1 second. So you will have to divide the whole time into very discrete time steps, which should not be more than a few femtoseconds. So of the order of 10 to minus 15 seconds could be your time steps. For each of the time steps, you have to compute the forces acting on each atom, and this will be governed by a molecular mechanics force field. So the molecular mechanics force field concept means that what is the nature of interaction of any atom with that of the surrounding atom. So you have to define those equations that govern those forces, and that's what is called as force field. So you compute the forces and you move the atoms according to those forces, and then the new positions and the velocities of each particles are then updated into the system, and they become the point of movement to the next iteration. Okay, so you define a time step, you compute the forces, you find the new positions and velocities, and then that's how you keep on iterating back and forth till you hit the total time span that you want to run the simulations for. I'm just showing a summary of the computational algorithm that is normally employed. So, like I said, you have your system, and you initially put your this could be connected polymer chain, and so each of these atoms positions are actually first fixed, and so your positions are given. You also give a velocity to each of these atoms. So you give the velocities, you give the initial positions of these particles, and you define the neighbors, so who are all the closest particles to each of the atoms. You get the values of the forces between each of the atoms, and based on these forces you solve the equations of motion, which will give you the new positions and the new velocities. Okay, once you have that, you move the time to the next time step, and you calculate any desired physical quantity that you wish to measure. You may not be there close to the total time that you have simulated, so because you've done one iteration. So once this point is reached, you go back and redo all these things. Okay, calculation of the forces, calculation of the positions, velocities, and stuff like that. So you keep on iterating till you hit the total final time of simulation that you wish to do. Over here, I also mentioned a point over here, which is perform the pressure and temperature control. We'll come into detail into this at some point of time, but what it essentially means is that you, during the movement of the atoms in the system, the the temperature of the system may increase or decrease, the pressure of the system may increase or decrease, because there's a physical motion which is happening. The heat might, the potential energies might go up and down. So it's an artificial constraint that you tend to put onto the system, such that it is more realistically acceptable, because the system, the material temperature, it doesn't increase and decrease on its own. So you keep a minor control on the system, although the system doesn't fluctuate too much, but to account for the fluctuations not to happen, so you kind of put temperature and pressure controls onto the system. We'll discuss how you do that, but these are essential steps that you normally use in terms of the computational algorithm, running the simulations, and finally ending the simulations with estimations of the desired properties that you want to do. So this is the general algorithm of molecular dynamics. Now let me go a little bit more detail into this step, which is primarily this equation, solving the equations of motion. So which is more of an integration algorithm. And so let's talk about it. We know the Newton's second law says F is equal to ma, and what we essentially can do is we can write force as also a gradient of the potential energy. Okay, so we can write force as a potential gradient of potential energy. Acceleration can be written as the derivative of velocity. So we have written this A is equal to Fx by m, which is equal to dv by dt. Velocity can be represented as the derivative of position. So we do that, and so using these equations, if we kind of integrate these equations, what we get is xi plus 1, which is the position of the particle at I plus 1 at iteration, is equal governed by xi plus delta t refers to the time step, and vi refers to the velocity of the particle I. Okay, so we've integrated it between iteration I and I plus 1, and that's what you get as the final equation. Likewise, you may integrate this and you get the equation for the velocity for the next step, which is governed by the forces acting on the particle at the previous step. So these are the standard equations that you tend to use. But time and again, people have tried to improve these integration algorithms, and we're going to talk about that in the some of the discussions forth. So what people have tried to improve upon these integration algorithms is some of the algorithms which are, for instance, a leapfrog algorithm or a leapfrog worldlet algorithm. So what you do is you essentially don't put the velocities that you get in the ith step, but you put it as I plus 1 by 2 step. So which is intermediate between the ith step and the I plus 1 step. So these velocities help give you a more accurate representation and accurate estimation of the position at the next step. Likewise, you find out the positions, the velocities at the I plus 1 at step using the already stored velocities at one step earlier. Okay, so you can get the velocities at the intermediate step. So these are little more accurate integration methods. We'll talk about more on these integration methods, but it's important to understand that these are the two basic algorithms, and people try and try as much as possible to improve these algorithms. Now, what is also important to understand over here that the Taylor series expansion, this is more of a Taylor series expansion, and the V is nothing but dx by the Taylor series expansion might have some more terms like d square x by dt square. It may have more terms of the function of d cube x by dt and stuff like that, and so on and so forth. The more number of these terms that you take in uh, estimating the value of xi, the better it is, the more accurate it is. But it also tells you that your work will get more computationally intensive and difficult, and also you will have to store a lot of these higher order derivatives to estimate the position of the particle. Now, so this is a tricky situation, and you have to understand SS based on the memory that your system has, the hardware has, based on the speed that your hardware can give. So, based on that, you kind of keep a balance between the accuracy and also your computational speed. So. So that's the first thing that I just wanted to discuss now before we go to the next slides on in terms of the improved algorithms. So before we talk about those improved algorithms, let's quickly talk about one concept, which is the stages. So there's something called as an equilibration stage and a production stage. Now, there's a little difference in among these two, is that when you start your simulations, you just randomly or chains or polymers, monomers in the system, and these might this structure might not be the realistic structure. Okay, these are some random positions that you have adopted, and while the molecules move according to the Newton's equation of motion, they will tend to get more and more equilibrated. Okay, that means they are trying to get more and more realistic situation. So the whole of the time till they keep moving and get a first frame where their positions and the velocities are more realistic and representative of the real-time material situation. So that's the point which we refer to as t is equal to 0 for the production stage. Okay, so after this stage where you have the first equilibrated frame, after this stage, whatever frames that you get, whatever new structures that you get, they will be referred to as part of production stage. So this entire stage is production stage till the time you move them to get first realistic structure. That time is called as an equilibration stage. So you tend to get a production several of these stages, several of these frames out of the production stage, and for which you actually do an averaging of these properties from these different frames. Now, these frames are nothing but different snapshots of your system. So, for instance, while you walk, someone can take different photographs of you and then club it to make a video of it. So similar to that, that different snapshots of your walking taken represent the way you walk. Okay, so and they give an average of that will talk about your walking aptitudes or walking behavior. And likewise, we average out several of these frames to get an average of the properties of it. So that's the production stage. So once you have equilibrated the system, you tend to produce or you tend to get the several structures of the polymers, which are averaged. The second thing that is important to mention is the concept of boundary conditions. If I'm not sure you have seen this kind of game which you used to do, which normally you call as the Pac-Man. So this kind of a structure goes around and keeps eating these things throughout the game. But what you would have seen is that while it goes around and let's say it comes from this side, you normally see in your game that it quickly comes from the other side. It comes in from the other side, and this is exactly what concept is used in molecular dynamics. The concept of boundary conditions or periodic boundary conditions, which means that if one molecule or one atom goes out from one part of the simulation box, then it has to come in from the other side at the same position, representing a similar behavior. Likewise, if it another molecule goes out from this side, it will have to enter from the other side, because that will enable a balance of the density of your system. It will also enable the macro level representation using a smaller simulation cell. Okay, so that's the concept of periodic boundary conditions. Now, what I've spoken, given you an example, is the concept of periodic boundaries. That means particles moving out will come out from the other side. There are other boundary conditions, for instance, no boundaries. So a polymer chain which could be surrounded by several, millions and billions of molecules, and so that could, you could try to understand how does a polymer chain evolve in billions of solvent molecules or an infinite solvent kind of an understanding. So what is its structure and what is its distribution functions and stuff like that. So you can get an understanding from the concept of no boundaries. You would have something like a fixed boundaries. So these particles which are thrown into the simulation box, they cannot go beyond these boundaries. So this is an example of fixed boundaries. There are situations like the intercalation of the particles, polymers within the clay boundaries or stuff like that. So you have those fixed boundaries in there. Likewise, you have the concept of periodic boundaries. So, kind of a protein molecule moving through the membrane, or kind of a drug molecule moving through the membrane. So, you could have the concepts of periodic boundaries, or the other concepts like gave pictures in the earlier thing. So, this is the concept of periodic boundaries, wherein particles moving to this side will have to come from the other side. The particles moving over here will have to come from the other side. So that's a complete periodicity in all the three dimensions, or in all the three directions, the X, Y, and Z directions. So that's briefly called as completely periodic or periodic boundaries. You could have a mixed boundaries concept also, wherein you may have no movement at the top and the bottom. So no particles can go out from the top and bottom, but on the left to right and from this area to the other area, you can have a movement. So it's a mixed boundary concept, periodic in two directions, but non-periodic in z direction and the minus z direction. So it's the concept wherein you can have a mix of the periodicity and fixed boundaries. So that's what is called as a mixed boundaries. Likewise, you could have infinite in Z. So that's the similar examples. You could have infinite in Z and a periodic in X and Y direction. So that's the example. So this I've already discussed, that you're trying to model an infinite amount of matter with a very small or finite simulation cell, which is the central simulation cell, which has been copy pasted in all around different cells. So for instance, in this case, these are 8 simulation cells which are surrounding the central simulation cell, which is the prime point of concern. Whereas in 3D, this number could be approximately 27. So there could be 26 molecules surrounding the central simulation cell. But again, even counting all these 9 simulation cells or those 27 simulation cells in 3D, the number of particles is still very, very much smaller than the billions of particles that you would find in a very small piece of a real-time material, which will have billions and billions of particles. So there's absolutely no match. But what we're trying to do is to represent the properties or evaluate the properties of those materials which are present, in real-time situations by a very small representation of micron level or sub-angstrom level simulation cells. So what you do is simulate a segment of molecules in a large solution by having repeatable regions. And when an atom moves off the edge, it will appear on the other side, just like in asteroids or the Pac-Man games that you have played in your childhood. This concept is also called as the concept of minimum image convention, and there is some computational jugglery that you employ in your periodic boundary conditions. So you keep on changing the positions of the particles through this computational mode. Given if you know what is the box size, so you can do that. So each particle interacts only once with a given particle. Potential calculations are run only on each atom's closest counterpart in 27 cubes. So this particle over here will not interact with all this cluster of particles. Okay, so you kind of give a cutoff range for this particle that you will interact with only a specific number of particles around it. This cutoff length is important because at specific cutoff length beyond that, the interactions are very minimal. They're hardly there. So you assign a cutoff range for interaction length for all these atoms, and you only consider the interaction with the atoms with only those atoms which are present within that cutoff length. Okay, so instead for this might have a cutoff length. So you only calculate the interactions with those atoms which fall within this cutoff length. So why is there a need for cutoff methods? And questions could be what should be the maximum cutoff for considering the interactions of any atoms into cell. Ideally, every atom should interact with every other atom, but this creates a force calculation algorithm of quadratic order. So that means if there are three atoms, then the number of calculations could be three square and stuff like that. Um, but however, we ignore the atoms at large distances from each other without suffering too much loss of accuracy. So, a very minimal loss of accuracy helps reduce the number of calculations that we will have to do. Imagine if this particle has to interact with all these particles, then imagine the number of calculations that we'll have to do at each step. Likewise, for all the particles, we have to calculate the interaction with all the particles. This also has to interact with all the particles, and this also, and this also. So you can imagine at in one single iteration, you will have to do a whole lot of calculations, which will make our simulations, kind of extremely slow. So this is the reason we ignore the atoms which are at large distances from each other and without suffering any too much loss of accuracy. Okay, so this is why we need kind of some cutoff methods to molecularly easen up our calculations and computation intensity is reduced. This is again the summary of algorithm that we have discussed, and so I think we kind of touched upon some of the concepts here. Now, some questions could be asked is how long should we simulate? Whether it should be 1 millisecond, few milliseconds, 1 nanosecond, 1 microsecond, 1 second, or stuff like that. Now, there are several choices which are given in the literature. So, primarily when I spoke about achieving an equilibration stage, so one of the requirement will be that we should at least simulate till the point that we equilibrate our system. So that is the first thing. And we should have our production stage, good number of frames in the production stage, so that we can realistically estimate and more accurately estimate our properties. Because if we have only a few frames in the production stage, then we will not be able to calculate the properties more accurately. So our equilibration stage has to be nicely planned. Our production stage has to be nicely planned. So that's how we do this. Different choices are used in literature. Example, movement of center of mass up to few times the chain diameter. So you kind of keep in mind how much the center of mass has moved. Okay, so you kind of see whether if it's a polymer chain, then the center of mass should have moved at least few times the chain diameter. So that is sometimes the criteria that people use in trying to understanding whether the in trying to kind of a limit people have put in terms of how much the equilibration stage would be considered, till how much you have to simulate. The next point comes that is important to discuss here is the concept of force field, potential functions, and force models. No, like I said, each of the atoms will be surrounded by different atoms. So, for instance, this carbon atom in polyethylene might be surrounded by several oxygen atoms or oxygen molecules surrounding it. What you will need to know, how does this carbon atom interact with oxygen atom, and how does this carbon atom interact with another carbon atom of the polyethylene chain. So you would need to know what is the intermolecular interactions between carbon and oxygen. You would also need to know what are the intramolecular interactions between the carbon-carbon atoms of the same chain. So, knowing those and defining those is what we term as the uh, definition of the force field. So, this is used to analytically describe the interactions among atoms. Different force fields may produce different results. So, I'll just give you a glimpse that there are different force fields which are possible. Okay, so there are different people have developed different force fields, and then they will give you different results. The accuracy will, however, depend upon your correct choice of force fields. For instance, if you're trying to understand liquid vapor equilibria and that force field has been determined based on the experimental semi-empirical relations which are more experimental driven, then in that case your force field has to be based on the source experiment which or the property which has been determined. So if you're trying to understand vapor liquid equilibria, and you will have to use a force field which is much more reasonable in defining or estimating the vapor liquid equilibria properties. So if you're trying to understand the thermal properties, then your force field should be appropriately used, which is apt, which is suitable to estimate the thermal properties. Likewise for the others. So computationally, the most intensive part of simulation code takes about 95% of simulation time. So force field calculations. I'm going to talk about the force field concepts in the next few slides. But this is nothing but it takes about the most intensive part of the simulation code. So like I said, you have to determine the forces between different atoms before you actually calculate the positions and the velocities of the next time step. So this force field has to be determined, but this is the most computationally intensive part of the simulation code. This is based on some quantum mechanical approximations, and it is parameterized with certain experimental or AB initio methods, which I'm not going to go into detail because that becomes a completely whole different area of discussion. But we're just going to, in simple terms, understand what the force field means and what are the different types of force fields which are available and used. We're going to talk about that. So, molecular mechanics force fields are inherent approximations for interactions of atoms. These have been improved substantially over last decade, but there are some limitations which are still left. Major force fields which are used by different researchers are a PCFF force field, which is nothing but polymer consistent force field. Then another famous one, which is also used by several researchers, is COMPAS, which is nothing but abbreviated by condensed phase optimized molecular potentials for atomistic simulation studies. Okay, so this is COMPAS. This is a very extensive force field, but little more computationally demanding. There are a lot of terms which have to be used, which are described in COMPAS, which have to be calculated. And so, because of the increased number of calculations in understanding interactions between atoms, your overall computational time might be more demanding in this case. The other force fields are charm, amber, OPLS, AA, and stuff like that. So these are several other terms. So what you have to essentially do, this I've already spoken, that you need position, momentum, charge, and bond information, and you have to solve the classic equations of motion. Forces between particles are derived from some analytical force model, and equations of motion are solved with finite difference algorithm. So this is F is equal to ma that you have. Force is nothing but gradient of potential energy function. So you may write dV by dr as equal to ma. So force is nothing but dV by dr, and m into a is nothing but m into d square r by dt square. Based on this, you can estimate the new particle positions. So we'll come to integration algorithm concept, but let's quickly talk about the fourth thing which I basically want to discuss first. The force field here refers to the evaluation of E bonded, which means
Hello.
hello.
Yeah, actually, I Just want to know that how to get these potential functions.
So these potential functions have already been estimated from either the energy position graphs, or they have been obtained from the experimental sources. So for
Suppose, Miss, if I can interrupt here, suppose I'm doing this, let's say, diffusion of solvent means polymer molecules in my polymer solution coating. So, means how can I get it? Because I just want to do something in this field.
right, right. No, so if it's a polymer molecule and you're trying to diffusion in what?
In solvent, actually, generally we are putting I mean the dissolving a polymer into the solvent just to make a polymer solution,
Yeah.
and then we are allowing it to dry actually to get the dry polymer film.
Right. So what happens is these there are some commercial softwares which are available which already have these defined potentials and the forces. Now these
Okay,
potentials
okay.
that I am talking about are this could be an interaction between, let's say, an acetone molecule and acetone molecule. This carbon of the backbone chain with the solvent molecules. Let's say if it is methanol, so CH3OH. These
So from the molecule to molecule combination, these values are known actually, you can
in
say.
fact not molecule to molecule but atom to atom. So this carbon
Atom
atom,
to atom, okay.
yeah, this carbon atom in your polymer chain, its interaction with methanol carbon, this interaction is already known, is already established, and the commercial softwares have all this information inside them. So you don't have to define many of these things. You just
Okay, okay.
yeah. So you just have to put these input raw materials into your simulation box, and you give your initial conditions, and it starts running.
Okay, sir. Okay, sir. Continue. Thank you.
Thank you. So, so just to describe that these potentials, at least the atomistic level potentials, are completely well known now. I think about a century has passed since 1950s. Not century. I would say about four decades, 5 decades have passed, wherein people have tried to get maturity in defining these atomic level potentials. So these are all well known, and they are well documented in literature as well as in software. So there's no need to worry about it. But what you need to worry about is what force field to be used. So, for instance, I was just trying to say that this is the several force fields which are available. So, PCFF force field is a recent introduction which is more specific to polymers. Compass also can be used for polymers, but it is little more computationally expensive. And there are then other fields. For instance, amber is more and charm are more frequently used for biopolymers, biomolecules, protein, tissues, and stuff like that. So you just need to have an understanding what force field to use, because those force fields have been defined for specific systems. So that is the understanding that you need to have before you run your simulations. So this is about the bonded, what I was trying to describe. So there could be the potential on any atom could be composed of several things. So it could be bonded with its nearest atoms, or it could not be bonded. So this bonded thing, you bonded neighbors, you would need to know what is the bonded potential. If it is not bonded with the surrounding ones, then you will also need to know the non-bonded force or the non-bonded potential. Okay, and the total force on this particle will then be a sum of this bonded force that it experiences and the non-bonded force it experiences from the surrounded atoms. Now, so now we'll talk first upon the bonded concepts. So, in case of the bonded neighbors, what are the different sub forces which an atom which has been bonded to surrounded atoms will experience? So, a atom could be bonded as a part of a chain. So you would need to know what is the total sum of bonded forces, or what are the different bonded forces that this atom will experience while being part of a chain or stuff like that. So there are three types of interactions. The one which I clearly showed that this is attached to this. So there is a kind of a bonded interaction which we call as stretching. So this bond may actually that I've shown, so this bond may actually stretch. Okay, so it may stretch or it may compress. So depending upon stretching and compressing, a specific force will act on each of these atoms. Okay, so a specific force will act on each of these atoms, and so you will need to know what is the amount of force that occurs on them. So that part of the force is called as a stretching along the bond force. Then the other force which could also involve is this bending of this angle. So these three atoms may together work such that these two may move closer. So this whole angle may decrease, or they may move in the opposite direction such that this whole angle may actually increase. So this is an angular potential, which means it's the bending between the bonds. So for each of these bonds, for instance, stretching part, there is an ideal L0. L0 when I refer to, which is a kind of an average or equilibrated bond length. Okay, so if let's say carbon carbon bond, it is 1.54 angstrom. If the carbon-carbon bond moves beyond, so if the particles move so that it becomes 1.59 angstrom, then a compressive force will act on them and it will try to bring it back to 1.54 angstrom. If the bond length at some point of time tends to become 1.4 angstrom, then these two atoms will be given an outside force because of this potential, such that they come close to the equilibrated value of 1.54 angstrom, because that's the most stable bond configuration. So this is how you define the stretching force around that equilibrium value. Likewise, the bending of this angle will also, this angle might also be at, let's say, 109. Okay, so might be a more saturated, more equilibrated bond angle, and any movement of these two atoms, let's say this is atom A, this is atom B, and this is atom C. So any movement of atoms B and C away from this equilibrium value of 109 degree will tend to bring these atoms back in such a way that the angle tends to remain close to 109 degree. So that's how you also define the bending between the bonds. You tend to define the bending potential between the bonds in such a way. Likewise, you have the third thing, which is the rotation. So this is nothing but a 3D rotation of this bond. Okay, so the 3D rotation between these bonds would actually make the bond, the atom B and atom B, move in the 3D plane. Okay, so a 3D movement of this bond between atoms A and C. So this is my atom A and this is my atom C. Okay, so any 3D movement of atom of this bond AC will make the atom B and D move in the space, and that's what we call as the torsional movement or the rotation around the bond. So this is called as rotation around the bonds. The This angle change is referred to as bending between. So you will need to know the bonded potential, which is a sum of the stretching bonded potential, a sum of the angular bending potential, and sum of the rotation along the bond potential. So you will have to have sum of all the three types of potentials to know the final bonded potential or get an idea of the final force on the atom A because of the surrounding atoms which are kind of bonding to which it has already been bonded. So this bonded force needs to be estimated at the first shot. Now there are different kind of equations which have been proposed, different ways this has been proposed. So this is the bonding potential. It's assumed like more like a spring, so kind of a Hooke's constant, or kind of a Hooke's law. So it's more of a spring potential which people have adopted to. So this B0 is nothing but the equilibrium length that I was referring to. In case of CC bond, it could be 1.54. If you see C double bond C, it would be around 1. I think 1.4, and triple bond, it would be around 1.3. So depending upon what bond we are talking about, this B0 can take that form, and this KB constant will also accordingly take that form. Because, for instance, in the case of triple bond, it's very difficult to move the bond, so K values will be very high. So this is what we refer to as the bond stretch, and this is a very harmonic kind of a potential which is available and people very frequently use to represent this bond stretch potential. Then, like I said, the other one could be the angular potential. So the angle might change from its equilibrium value, which could be 109 or whatever, any of the angles. So any movement away from this will lead to a harmonic force or a kind of a Hooke's law force applied onto the in bonds around it or the atoms around it, and such that the bond bending doesn't get too much beyond, and it comes back to its position of 109 degree or whatever is the truly present. So that's the angle bending form of potentials, which also people have proposed as more of harmonic potentials. The other one is the rotation along the bonds potential, and in this case, people have proposed. So if he represents the kind of a torsion value, so this has been represented in terms of example in ethane. This is represented by this equation. In butane, people have represented it in a different way. Okay, I could probably go in detail and talk about how have these equations come up and what are the different forms of these potentials, but uh, that will be too much for this part of the talk. So we'll avoid that, but you can assume that there are different kind of a dihedral forces or rotate along bond forces and different angle bending forces and the bond stretch forces. So of the type that I have shown. So once you evaluate all of these, you can just sum these numbers for each of the atoms, and that gives you the total value of the bonded potential that each of the atom will kind of an experience by the surrounding bonded atoms. And this you do for each of the atoms which have been bonded and for every iteration. So once you have found this out, you have done one good piece of the work in the fact that you have found all the entire cluster collection of the bonded forces. What is left is now the non-bonded forces, and the non-bonded forces is nothing but a sum of the van der Waals forces and the sum of the electrostatic forces. So you will have to find out the van der Waals forces and the electrostatic forces, which so electrostatic may be present, may not be present. Van der Waals is in general most of the time present. So you find this out, and van der Waals potential is normally generally of this form, which is 4 epsilon sigma by r raised to the power 12 minus sigma by r raised to the power 6. So as the atoms tend to move towards, so this is plotted as a function of distance, and over here you have the potential. As the atoms will move towards each other, the potential tends to get negative, which means that the atoms are experiencing a positive attractive force. When you tend to move very close, the atoms tend to move very close to each other, they start repelling each other, and they have a very sudden, very high amount of repulsive force. And this whole and the curve is represented by this form of potential. So given any value of r, you can find out what will be the potential between those two atoms. So this is a very frequently used potential term, which is basically actually a sum of sigma by r power 12 curve, which is this curve, and then sigma by r raised to power 6 curve, which is this curve. So when you sum these two curves, then this is the structure that you get. This is the one which is the overall, this is the repulsive part, and this is the attractive part. So attractive part is primarily coming because of a nucleus of one atom interacting and attracting the electrons of other atom, and the repulsive term is coming because of the repulsion happening between the two nuclei, and also between the electrons of the electrons of the two atoms. So this is how the bonded or the Lennard-Jones potential comes out. And the form of the Lennard-Jones potential comes out. Now this you have to calculate for almost all the atoms, and this is a little tricky and difficult calculation because you are giving sigma by r to the power 12 calculation, and so that may be computationally very intensive unless you make those computations in a little smarter way. Okay, and that's one reason is for using the cutoffs as well. There's another way of representing the Lennard-Jones potential, which is A by r raised to the power 12 minus C by r raised to the power 6, for which the A and the coefficients A and the C's are already known to you. So these are available for different data for different atom types. So these are already been experimentally derived. So with already given these constants and already available as part of the database of any of the softwares, you can quickly find out between different atoms what are the Lennard-Jones forces. You will also have to derive the one which you call the electrostatic potential, so which we have read in our 10 12 classes, which is force is nothing but k q1 q2 by r square, and k is nothing but 1 by 4 pi epsilon, epsilon being the permittivity of the medium. So this q1 q2 by r square are the charges between any of the atoms on one of the materials, and so given those, you can calculate the forces and between those two charged atoms. So once you do that for the entire cluster of all the particles in your simulation box, you are ready to know what is the non-bonded, because you have calculated the van der Waals or the dispersive potential, and you've also calculated the electrostatic potential. So some of these two is referred to as the total E non-bonded potential. Okay, so there are some methods in electrostatic which I'm not going to go into detail, but then there are methods called as Ewald summation method, stuff like that. So you can then there's a particle mesh method and a fast dipole method which you can use to find out the electrostatic potential in a much more computationally easy format. So you can do that also. Now the next concept comes is the use of cutoffs. So okay, so the how and why do you use the cutoffs? So this is primarily applied to van der Waals cutoff. The van der Waals cutoff, if you see the real time plot, is the one which I've shown in black over here, which is this one. Okay. Now, so actually it will go like this. It will go like this, and it will probably touch zero at about 25, 30 angstrom or something around that. But if you take more number of atoms, so if you keep the cutoff as 25, 30, then the number of computations that you have to do for van der Waals for each of the atoms is going to be very, very large, because it's now a very bigger sphere to handle. So that becomes a tricky case. So you tend to do a cutoff thing, and these are different ways. The first is the truncation. So you cut off the calculation at a predefined step. So for instance, the red one. So at this point, you do a truncation and you say that's it. I will not go beyond this. Okay, so that's a spontaneous truncation. The second one is a shift, wherein you see the green one has been, so this was the original one. You have completely moved the green one vertically upwards. So this whole curve has been moved vertically upwards such that it touches at this point the zero. Okay. So you have completely moved the entire function vertically upwards so that it is zero at a specific cutoff distance which you want. So in this case, for instance, a cutoff distance that we have chosen is around 12, 13 angstrom. The next one is switch, and the switch says the blue one. So you go as per the Lennard-Jones behavior till a particular point of time, and beyond that you actually you kind of taper it down as compared to the natural taper. So this was the natural taper, but you taper it down very quickly. So that's the quick tapering, and that's what we call as the shift. Okay. I'm sorry, that's what we call as the switch function. Now, when we do all these cutoffs, we are doing these things unnaturally. We are not using the right format of the van der Waals, and so a tail correction needs to be applied. Okay, so this tail correction has to be applied into pressure. Okay, so this is the format of the pressure tail correction. At every instant of iteration, you have to recalculate the pressure, because, like I said, the pressure and temperatures might marginally change. Now that pressure may govern the movement of molecules again. So what you do is you apply this pressure tail correction to the system so that this non-natural thing that we are doing is taken care of. Any questions that you may have?
Yeah, actually, I want to ask, we did all these molecular modeling and we are doing tail corrections and all these things. So this we did totally a computational part, right?
Yeah.
So how do we make sure that this would really would happen in a real practical case?
Yeah. So, Dr. Raj, I will let me finish this molecular dynamics part. When I jump to coatings, I would show a one-to-one mapping between the simulation part and experimental part. Okay, so you may partly do
Yeah,
your
yeah, yeah,
experimental
yeah.
part also, and you may try to see whether things are matching nicely or not. And in most of the cases, these force fields have been so immaculately made now that in most of the cases you find your properties experimental versus simulation matching in most of the cases.
Okay, okay.
So I will give you some glimpse of that once we discuss
Sure,
this.
sure, sure.
So, next part, I'm going to quickly touch upon integration algorithms, why and which one. So, these integration algorithms that I was saying will depend upon several things. Like I was trying to describe that we may have to calculate the second order and third order derivatives. So, you have to make a compromise between different things. So, you will need memory space if you're working with more second order, third order derivatives in integration algorithm. Your speed might go down, and then the third case might be the stability. So the integration algorithm, which is primarily governs the calculation of the positions and the velocities, uh, that will be dependent upon these factors. So why the choice is important? The integration algorithms are important because if you choose a larger time step, okay, then you may reduce the effort and computational time which is needed. But this can only happen if your algorithm is robust. If your algorithm is not robust and if you've taken a larger time step, so normally you take 1 to 2 femtosecond as one of the time step. If your algorithm is not robust, then you are actually going to have instability into your system. So by the concept of instability, I mean that some of the molecules which are actually bonded may appear to break away and go to infinite spaces. So they might just go out of your system. Okay, so these are the problems which may happen if your algorithm is not robust and if you tend to choose a larger time step. Now the question arises how to achieve accuracy with larger time steps. What you can do is you can store higher order derivatives. Okay, but then this requires increasing amount of memory space because you will have to store all those derivatives. The energy conservation is important. Higher order algorithms show good energy conservation at short times, but give long-term drift. So the drift of the center of mass might happen. So the algorithms like Verilog type algorithm are chosen. So this is what I was trying to say that in this case R is nothing but X that I mentioned in my previous thing. So the position of a particle at any time step at any time t plus delta t is governed by what was its position earlier, what was its velocity earlier, what was its acceleration earlier, what was its third derivative of position earlier, and that's it. So the more number of derivatives that you take, the order of your error goes down. Now, mind it, I am writing delta t to the power 4 is the order of error, but delta t in this case is less than 1. So anything which is less than 1, the higher the power I have over here, the lower is my error. Okay. So when you go and keep on including more and more terms in getting the position of my particles, if you keep on taking more and more of these terms over here, then you get more and more accurate because this term goes, this 4 goes to 5, 6, and so and so your error goes down. But the problem that happens is that you will have to store all the velocities, you have to store all the accelerations, you will have to store the third order derivative, you will have to store fourth order derivative, and so on. So forth. And it is not only that you have to store, you have to even calculate them, which becomes a pain. So there are several algorithms which people have proposed. For instance, the truncated or Euler's algorithm. Okay, it is good in its term that the error is of the order of delta t3. It doesn't require computation of third order derivative, but it is not very good because it does not preserve the energy, and the energy drift might happen. So the particles energy levels might increase beyond the starting initial energy levels. So that might not be a good case to handle. Then these equations require AT, which actually means the use of forces over here, because AT is nothing but FT by M. And you will also use forces like LJ potential. They have powers of 12. Okay, so when you use that, then it would make Euler horribly slow, or even worse than usual. So there are other algorithms. I will not go into complete detail of this, but then some of the numerical techniques which you would have read in your different courses include the Rangakotta method, the midpoint algorithm method, and several other methods are so a compromise between different things could be made depending upon what algorithm will help you in achieving the desired property or the desired system behavior. So you may adopt to that, or something which suits your hardware requirements also. So based on these, there are several things. You could estimate the velocities using this. Okay, and now, estimating the velocities using this, so there's one concept here. Let's say if you're using this equation for estimating your positions, you're working with an order of delta t to the power 4. And if you use this concept to estimate your velocities, you're working with an order of delta t squared. Now, since you have to use both of these equations in one equation is giving you a very nice, very small amount of error, because delta t to the power 4 is much smaller than delta t raised to power 2. So your errors over here are much smaller than your errors over here, which means it's like it's like a it's like a ship wherein people were sweetly sitting, and an elephant come into it, and then the entire people drown. So this VT equation will drown the equation of position also, because ultimately this VT is going to be used over here. So despite that you made all the efforts in calculating the positions using order delta t4, you are suffering because you have a velocity calculation which is of the order of delta t square. So this equations, these concepts or the algorithms of the Wallet algorithm may show some limitations. That's why we people adopt for the leapfrog algorithms, which tend to improve the velocity estimations. So these are some estimations, kind of a Wallet algorithm, kind of an algorithm where you find RT plus delta T, you find RT minus delta T, and then when you sum these up, what you get, a summation will give you this, and this gives you this equation, which means this equation is hardly dependent on velocities. So this is another way, which is the Verlet algorithm, where people kind of ensure that they don't use a velocity at all, unless in this case you are using velocities. But the final equation that is used computationally is actually not making use of velocity at all. It is only making use of the positions of the particle at the previous time step and the position of the particle at the previous to previous time step. So that just helps. So you can bypass choice of velocity, and your order of error is also considerably very good. So that's the advantage. So there are some pros and cons. Like I said, memory, CPU. You have to look at the long-term energy drift. You have to look at the stability of the or the robustness of the system. Uh, 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 Cons are that it is not as accurate as Rangakutta, primarily because Rangakutta uses more number of terms. It is not good with larger time steps, because efforts are needed to compute forces on particles more frequently, and we never calculate the velocities in this case. So in case if you need the velocities calculation, then you may probably this may not go down nicely with someone, because velocities may be needed, for instance, in calculating the diffusion coefficients of particles and stuff like that. Okay, so I will just quickly come to this part uh, where the concept of leapfrog algorithm. बचपन में सब लोगों ने किया होगा कि this guy jumps on top of him, this guy will jump on top of him. So that's the concept of leapfrog. First you jump on top of me, then I'll jump on top of you. So that's the concept of leapfrog algorithm, which is an advanced level to the algorithm I've spoken earlier. And what you do is you find out the velocities at t plus delta t by 2, which is half the time step. using the velocity at minus half del t by 2. And you find out the position using this velocity. Okay, so once you find this out, you find using this half time velocity. And so once you have found this out, you can find this positions. Now, this uses explicit velocities. Disadvantage is that while you are calculating the positions at t plus delta t, you are calculating the velocities at t plus delta t by 2. So there's a kind of a disagreement between the calculations of velocities and positions. So you need to have your velocities approximated in a better way. So what you do is you may avoid this issue. Just give me one second. Sorry. Okay, so the one point the issue which was that velocities and positions are calculated at different time steps. You do an approximation with velocities, and you are able to improve the velocities by doing an average over these two time steps. So that helps you improve the velocity estimation. Okay. Then there are other algorithms which help to improve both the position estimates and velocity estimates, known as Beeman algorithm. And then there are several other ways by which you can do that. Um, I would probably not go into detail into that at this point of time, but there's something which I said that you have to run the molecular dynamics at different conditions. So you may probably have done the experiment at, let's say, 273 Kelvin, and you would like to hold the molecular simulations at 273 Kelvin. In that case, you tend to couple the system, and you use kind of some hypothetical thermostats, okay, and which tend to keep your system temperature under control. We'll quickly go into these details. So there is a Berenson thermostat wherein once you have found out the velocities of the system, you tend to scale the velocities of the system every time. And so this will help that the temperature of the system does not increase. So what essentially you are trying to do is you are trying to connect your system to a heat bath. Okay. So as soon as your system loses heat, some heat will flow from the heat bath. If the system gains heat, then some of the heat will go from the system to the heat bath. So this is the whole concept, and there are different thermostats like the Anderson thermostat, and then we've got Moose thermostat, we've got stuff like that. Now, all these thermostats have one criteria. They tend to, so you have to use some parameters which define the coupling. So, if the coupling is very strong, any small increase in the temperature will quickly go away to this heat bath. Any small reduction in the temperature will quickly come to this. So that's more of a coupling constants that are normally used in defining these thermostats. I'm going to give you some pictures of this. So for instance, uh, okay, so these are not here. I will talk about barostats. Okay, so that is the whole concept around thermostats. Then there are barostats. Now, the barostats mean that you would like to keep the pressure of your system constant at, let's say, 1 atmosphere. So you do the coupling of your simulation cell in a similar way. You couple these to your external baths, which are now pressure baths, and then there might be coupling constant. So this the system that I showed, so there might be coupling constant. So instead of heat bath, it may be a pressure bath in that case, and then their coupling will be controlled by different constants. The example that I show over here is this. For instance, you may have a coupling constant which might be too low. You may have a coupling constant which might be too high. So what you see over here, any change in the pressure of the simulation cell will get controlled either it will be a very tight control, or it will be a loose control, depending upon what is the cell time constant that you have chosen. Okay. So these are the some of the barostats. Then there are other barostats like Berenson barostat, Anderson barostat, and stuff like that, which will have different terminology. Like it may use a decay constant, it may use stuff like decay constant and cell time constant. So you have to feed in these constant values into your system software and start running them. Okay, so these are some concepts around the thermostat and barostat that you may use to control the temperature and pressure of your molecular simulation cell. So this is around the ensembles, which is you may need to control the number of molecules, you may need to control the volume of your system, you may need to control the energy of your system. So that's what is called as a microcanonical ensemble. You may need to control molecule number of molecules, volume and temperature. It's called a canonical ensemble. And if you control pressure and temperature, it's called an isothermal isobaric. And if you want to control chemical potential and velocity, volume and temperature, then it's called as a grand canonical ensemble. So depending upon what you want to do, what situation you want to study, you may take any of these conditions and accordingly have your either a temperature bath or pressure bath or energy bath and keep these conditions under control to evaluate the properties of your interest. Any questions till this point of time? Hello, Dr. Raj, am I audible?
Yes, you are audible. Actually, people are understanding. This is not a common computational technique,
Right.
so people are understanding it actually.
Okay. Questions that we have to answer now. Now, the second part that I would like to touch, because we're close to the time, I would not go into the concepts of limitations and the accelerating molecular dynamics because this we can probably talk at some other point. But these are some softwares of DL Poly, Material Studio, Amber, which are available. Among this, the Material Studio software is available freely, is available commercially. DL Poly, Gromax, and Amber, Charm, and Lamps. These are most of these are not available freely. So these are available freely, open source. Only thing is the commercial softwares are there, which are Material Studio and others. So people have to purchase. Then for visualizing, there are several softwares, and most of these are freely available over the internet. VMD, Ovito, Rasmol, and Site. You can just download these, and only thing is you need to give the data file, you need to give the trajectory file to make your videos and visuals. Okay, so there are good number of packages which are available for visualization of your results. Now, let me touch upon quickly upon my other parts, which is how we apply molecular simulations in evaluating properties of composites. Um, I will probably not be able to touch upon all the properties of composites here, but at least I will try to pick one or two properties for each of the cases of composites and coatings. Just a quick view of polymer composite. A polymer composite is nothing but there is a continuous phase, which could be a polymer, which could be a metal, which could be a ceramic, and there is a discontinuous phase, or also called as a reinforcing phase, which could be glass fibers, carbon fibers, polymer natural fibers. Now, these could be still short fibers or particles, spherical particles of fibers. These could be continuous, which means long fibers. They could be uniaxial, okay, long fibers, or these could be in the form of textile. So these are two parts of a general polymer composite material: a continuous phase of a polymer and a discontinuous phase, or which is also primarily called as a reinforcing phase. Now, the reason reinforcing is because these fibers that you see or the particles that you see, they tend to strengthen some of the properties of the base polymer. So this is the general concept of polymer composite. So you have a whole range of polymers. You have PP, you have LDP, HDP, polystyrene, nylon 6, nylon 6. several of these polymers and their different properties. So depending upon your criteria of use of or making a product, whatever choice of these properties like density, elasticity, tensile, impact, whatever property fits you, you may choose that polymer. Likewise, you may choose whether you would like to have choice of natural fibers like flax, ramp, hemp, jute, sisal, coconut, whatever, depending upon their tensile strength, or you may take synthetic fibers like glass, aramid, and carbon. Primarily, the carbon is most stronger among all of them and most capable in terms of giving the best properties. So, carbon fibers can give you strengths as high as 3 to 5 GPAs, 3 to 7 GPAs. The modulus could be as high as about 220 to 40 to about 500 GPAs. This is in contrast to the modulus that you have for the general fibers, natural fibers, only few GPAs. So depending upon the property that you want, and the cost obviously will come at a price. These synthetic fibers will come at a price, so you tend to take that fibers. So, having given that brief description about how to make your reinforced polymer composites, can we use molecular modeling and computational tools to find out what would be the strength of these composite systems? So what we show over here is a way wherein you can try to so there's an experimental which is performed wherein you try to find out how strongly these carbon fibers or any of the fiber is present in the matrix. So how strongly are these fibers that I mentioned? How strongly are these fibers actually present in the base matrix? Now, the way this is done is you kind of put a polymer micro droplet on one of the end, at one of the end, and you try to pull this fiber uh, uh, through these very kind of a small shearing space which is there. Once when this is pulled, you try to estimate how much is the strength which is needed. Okay, and normally you will get some kind of curves like this. So you try to understand how is the fiber debonding and moving away from the matrix. So you will first get a fiber matrix will remain intact, then the fiber will start debonding from the matrix, and then it will slide off. Okay, so this movement of this fiber from this polymer, when you do that, you try to capture the force plot, try to capture the load versus displacement plot. So this is what you get. And also, this gives you a kind of a strength, an idea about the strength of the polymer, adhesion between the polymer and the fiber. Now, this is exactly what we have tried or some piece of the simulations, and several other researchers are also doing this, wherein first they make the polymer matrix. Okay, so you simulate this polymer matrix, and then you make a representative carbon fiber. Now, as such, carbon fiber is a cluster of several, can be assumed as a cluster of several graphene sheets. So that's what we have done is we've kind of made a lot of these graphene sheets collectively together. And then we place this polymer matrix on one side of it and similar polymer matrix on another side of it. And we try to pull this off. Okay, and this gives us nothing but through the computational calculations, this gives us nothing but an idea in terms of an interfacial shear strength which is represented by tau, which can be obtained using this relation, and it is nothing, it is speaking nothing but what is the total internal energy difference, mm, uh, uh, okay, between the whole system when it is at this position, at let's say when it is completely come out from the matrix, okay, at this position, minus when it is at the starting position. So you find out what is the delta E at this position, and you find out what is the delta E at the initial position, divided by L and B. L and B are nothing but the two length and breadths of this system. So when you find this out, you get an idea of the interfacial shear strength that this carbon fiber is going to feel when it is present within the matrix. Okay, and they're very interesting results in terms of what we have got. So we were able to very nicely find out this maximum interfacial strength at which it begins to debond. Um, this is how it happens. So you're pulling it out and you trying to study the total interaction energy differences at this point versus when it is present over here. So you find this out while the simulations proceed. Then the second part of the work which we have done, and some of the researchers are also moving in this direction, is you kind of coat the carbon fibers using CNT. So that's a very frequently being part of the work which is being done. You coat the carbon fibers using CNT, and you try to understand whether that interfacial shear strength has increased or decreased or what has happened. So once you start pulling this, so you do the same pulling phenomena with this case also, and you see what you try to capture what are the internal energy differences, so that you can get the interfacial shear strength. So these kind of understandings you can evolve through the making the molecular simulations. You can find out how nicely the fiber or the functionalized fiber is adhered to the matrix. Now, the next pieces of work people are doing is these carbon fibers. People are coating with different, chemicals. They're trying to incorporate the COH functionalization. They're trying to incorporate NH2 functionalization, trying to incorporate OH functionalization, and then trying to observe what are the levels of the interfacial shear strengths. So some results are part of the lab wherein we found that NH2 functionalized 6% is much better than the base matrix with carbon fiber, and it's even better than the CNT functionalized and then NH2 on top of the carbon fiber. So using these kind of results, you kind of get an understanding without even chemically synthesizing these things. You get an understanding in terms of what kind of functionalization will work better in what matrix. Okay, so because these fillers and the fibers and the base matrix are going to interact completely in a different way depending upon what kind of van der Waal interactions or the polar interactions are happening. So a lot of these things will get governed, and you don't need to you don't need to run those experiments and use the chemicals. Everything is there in terms of the force field, and you can estimate many of these properties theoretically. Some of these results are very interesting in terms of they kind of give a direction what should be done. So this part is what we have spoken. One piece of the work which we are also doing is that CNT, there are several defects which are possible within the CNTs and also the carbon fibers. So you can even kind of molecularly simulate those defects into the system and get an understanding whether those defects will actually help improve your interfacial properties or they will actually decrease your interfacial properties. So all those defects sometimes are actually useful, sometimes they are not. So you can tailor, you can design your defects depending upon what your simulations give you the directions. So let me touch upon this quickly now, probably another 15 minutes, this part which is on the coatings development. How we can molecularly model the coatings, how we can evolve their properties, estimate their properties. So let me first quickly touch upon the fundamentals. Most of the surfaces are hydrophilic or hydrophobic. There are others, lipophilic also, but hydrophilic and hydrophobic. Nature has many hydrophobic and super hydrophobic surfaces. And the hydrophobicity or super hydrophobicity is dependent not only on the chemical composition, but also it is dependent upon the texture that the surface has. Okay, so this is what nature has, and we people in the labs are also exploiting that. We have employed this understanding from nature in evolving some self-clean coatings, and we're going to show some results using molecular simulations. So the self-clean coatings are several uses for automotive, to our households, to coating of the solar panels on our anti-reflective coatings on the our specs or in the mirrors. and even in the aerospace industry. Now, this is the concept superhydrophilic and the superhydrophobic. Superhydrophilic will that film will go completely as one shot, whereas superhydrophobic, once rain comes or you wash it, then it will bump off across as one as molecules, and the fluid will bump as molecules, and it will take away the dirt. So the dirt mechanism works nicely with the superhydrophobic. That's what researchers have indicated. And so this is a lotus effect. So while the water droplet is coming down, it is taking away all the dirt which comes on it. So it works like a sticky ball which comes down and takes away all the dirt particles. And this is what exactly is found in the lotus structure also. There are epidermal cells, there are epicuticulars, waxes. The waxes do the hydrophobic effect, and the epidermal cell structures actually make that hydrophobic effect. So it's interesting to see that there's hydrophobicity which is brought by waxes, but presence of these structures in this way, the kind of a cylindrical structures, which is the texture building. So it's a cumulative effect of the chemical structure and the chemical format, and also the surface topology which comes as a result of epidermal cells. So the cumulative effect brings about this kind of a superhydrophobic behavior. So then there are other biomimetic surfaces. There's a rice leaf inspired surfaces which also do the same effect. Mosquito eyes, for instance, have a very interesting anti-fogging effect. Okay, so in the mosquito's eye, mosquito is able to see very clearly in case of moisture or in case of rainy season. So it's got some of these surfaces, micron and nano level surfaces, which keep its eyes very clean and transparent. Then there are some butterflies, effects, insects, which are also inspired in superhydrophobicity. Rose petal also does the same effect. Okay, but interestingly, it not does not let it sit. So it sits like this, but it when you turn it back, it doesn't fall off. So it's got an adhesion also, but it doesn't let it completely sit nicely completely. So it doesn't let us fill form at its surface. So rose leaf petals. Then gecko feet also has similar kind of a behavior of a micro patterns and the nano patterns on its surface. And that's exactly what people and the research is driving on the lotus leaf or the rose leaf effects. I will not go into details about these fundamentals, but this is basically the equation which is normally Young's equation, which is normally used to find out the contact angle. So, okay, so the contact angle is nothing but the this angle. Okay, so this is the contact angle which you have to drive. And if this contact angle is greater than 150 degree, then you say that the surface is super hydrophobic. And if it is in between 100 and 150 degree, then it is termed as hydrophobic. Now, people are trying to target durable super hydrophobic coatings, and this is what we have tried using molecular simulations. So these are some of the equations that you tend to use. I'm not going to go into details. Some Wenzel model, Cassie model, and then transition between Cassie and Wenzel states. But let me just talk about the structure. Okay, so the whole concept goes is that you have to have a substrate which provides you some hydrophobicity, and you need to have some kind of a dual scale roughness. By concept of dual scale roughness, what I mean is you're going to have some of these micron sized particles, which could be anything. There's several chemical and source particles which are available, and then on top of these you could have nanomaterials or quantum dots like C and T and Z. Now, this dual scale roughness, which is the micron size roughness and the nano size roughness, actually brings about a tremendous increase in superhydrophobicity or the hydrophobicity. And that's what exactly we've tried to do in our experiments and simulations. And I will try to discuss that. The base matrix, so this is the base matrix or the substrate. We've chosen a PVAC grafted PDMS. And so this is your PDMS, and this is your polyvinyl acetate. And you make the molecular simulation cells of these, okay, And on top of these molecular simulation cells that you have made, you try to put the fluids, which could be water or oil or whatever, and you try to find out what is the contact. Okay, so that's the whole molecular simulation inputs which go over here. You also do the experiments, you synthesize, you may also synthesize these, and you may also find out the contact angle. So this is what an experimental evaluation of the contact angles. The results show that whatever we have found as part of the simulations in terms of contact angles, these very much agree with whatever has been found experimentally. Okay, so this is a very classic use of molecular simulations to understand the surface behavior and also evaluate the contact angle properties. We have also found out how does this coating may actually interact with any of the substrates. Okay, so this is an interfacial interaction between the coating and the substrates, and this also dictates how much the coating is going to interact, how much will be the durability of that coating, how much nicely it will be adhered. So all this piece of information is motivated using molecular simulations, and many of the coatings that screening and optimization that you can do using all these things. So these are some of the successful publications that have come out as part of this piece of work. um, you have just to touch about modeling, you will have to, like I was saying, you have to describe the force field. So this instance, for instance, you have to define how does a motor model charge parameters are there, what are the bond lengths and stuff like that. So all this you have to feed in into your molecular code or your molecular software. Then what you have to do is you have to use some of these atoms, you have to make a simulation cell, and then using a specific module you make a water droplet, and then this you have to make the base matrix. So you use the polyvinyl acetate molecule, you make an amorphous cell, you make a layer of it, and then you make a supercell of it. And once you have done that, you put this water droplet on top of it. Now when you put this water droplet on top of it, it sits and it equilibrates and finds a specific contact angle. So it equilibrates in structure. I'm going to show you some of the pictures, which is the non-annealed structure pictures of, you see that it is falling and then kind of finding an equilibrated contact angle. This is a much better annealed structure, which we found useful. So this water droplets fall, and then they form an equilibrated contact angle. Okay, so you capture what is the contact angle there finally. These are water droplets on the left hand side, and on the right hand side, when I say OCA, it is nothing but oil contact angle. So how does oil behave? So the oil falls, and then it finds an equilibrated contact angle. Okay, so these are different assessments that in terms of simulation time, the contact angle decreases, and then it tends to saturate, both for oil and water. And then this is the effect of the droplet size on the contact angles, both the WCA and the OCA. So you see that beyond a box size of approximately 25 angstrom, the contact angle saturates. So it is always good to take droplets beyond 25 angstroms. This is the software that we have used, and this is these are the molecules and a general protocol. I would not go into complete detail into this at this point of time, but what we could find out is we could do an analysis of glass transition temperature, durability, we could understand interfacial tension, we could understand surface energy, and so these are different protocols. Then we can estimate system density, we can estimate, so we can do all these we can even do a blend compatibility analysis between two base matrix polymers using DPD. We could even use Mesodyne, a kind of a simulation software where you can see that whether there is going to be a compatibility or incompatibility between the base matrix polymers, and likewise you can capture the contact angles. Now this is interesting in terms of the contact angle estimates are very much closer. So if you look at the simulated numbers versus the experimental numbers, these numbers are very close. So the point I wanted to tell, that your experiment and simulation normally go hand in hand. And if you can't do experiments, then you can probably definitely kind of predict what will happen, because your force fields are now very accurately defined. These are some other properties as collectively as a function of weight percent of one of the polymers in the base matrix. Um, so you can try to screen, you can try to optimize your coating formulations, and this is where you can even find out the glass transition temperature of polymers, of your base polymers, because when you plot specific volume of the polymers as a function of temperature, then the specific volume will suddenly change at a specific point. Okay, and you capture that point. That point is referred to as the glass transition. So you can do it for several systems. Then you can even find out compatibility. So these are dissipative particle dynamic simulations. The green and the blue, they are much comfortable over here. Whereas when you increase the weight percent of one of the polymer into another, you find that they kind of tend to get incompatible. We also did some results with different hydrolysis content of polyvinyl acetate, and with larger content, you see that the numbers are not very good. The visual representations indicate that the incompatibility happens. So you can also try to understand the compatibility issues, whether they're going to happen at specific concentrations between two polymers, and what concentrations will they happen. So these are general thought processes around that. You can evaluate Flory-Higgins interaction parameter. You can evaluate transparency of your coatings, and and then you can also. So this is the water contact angle. So these are the numbers that we have shown, the simulated numbers versus the experimental numbers, and they're very close for some of our systems that we have considered. Most interestingly, I would like to show you that the optimized coating formulations that we have made, and you can be using these molecular simulation techniques, we have made the final coating formulations. Since the whole thought was to make self-clean coatings, I would just end now with this video for you, which clearly shows that the self-clean coatings definitely work based on the whole lot of theoretical work which has gone in, and the theoretical understanding which has come out, and the theoretical optimization of the base formulation and the surface dual roughness. This is one such example based on the dual scale roughness that we has created. Just look at it, that what we have done is put a coated slide over here and an uncoated slide over here, and then we're going to put dirt, and then we're going to wash it away with water. So just have a look how things work. So first we're going to put dirt. Left side is coated, right side is not coated. We put a dirt made up of carbon black and raw dust. And this carbon black is very uniformly sprinkled on both the ends. And then we kind of throw water on top of it. And you see on the left hand side, which is coated, the dirt comes out so quickly. Whereas the right side, the dirt tends to stick or tends to be there at the surface. So it is still there on the non-coated slide, right hand side, it is still there and not coming out. So that's a visual or an experimental understanding of the self-clean coating, which has been driven using molecular simulation. So summary to conclude, a significant valuable tool, molecular modeling and simulations can help understand and evaluate the material properties. As a computational analysis, we can estimate properties of polymer composites. At least we can do a very good understanding of the interfacial filler and matrix adhesion, and we can compare composite with different functionalized fillers and different concentrations. Molecular simulations may be also successfully employed to understand the structure property relationships of coating formulations and to also screen coatings with optimal self-clean properties. So, in this piece of presentation, I've tried to use and demonstrate the effectiveness of molecular simulations in kind of estimating properties for composites and coatings. There are several other examples which you can also employ, such as in the area of adhesives and blend miscibility, compatibility, and stuff like that, which probably have not got a chance to touch upon in today's presentation. These are the list of publications in this relevant area, which my student has nicely been able to bring forward. Um, and these are the list of most pertinent experience references to the work I've shown. And thank you, and really appreciate the organizers of this workshop for giving me a chance to present to such a good audience. Thank you to all. Thank you to the audience, and thank you to Director and IT Jalandhar for organizing, helping organize. Thank you.
Yes, sir. Thank you very much. And uh, actually, I learned from here a lot of things, but as you know that for a beginner, if you want to start something, you always have a lot of questions in your mind, how to get this, that, and everything. So, so is there any means, as you said, the Material Studio is the paid software. So compared to that, all freewares which are available. So would be able to do some reasonable work using those free software?
You can do if your systems are very simple. If your systems are simple, then you would be able to do. If your systems are complex in terms of you saw that we tried to make the droplets and then put those droplets on top to the of the substrate. You also saw that we made some kind of a nanoscale roughness and a micro level roughness onto the substrates. Now, some of these things, as per my understanding, might be little tricky with the open source softwares. It is probably not that you won't be able to do it, but the commercial software that we have has made our work and task little more easier. So that is the whole point, that if you can learn, go into the depth of those open source softwares, and then you have to learn from the web by connecting to several groups who would have used those open source softwares. So my experience has been that the software that we have employed is much more customer specific and easy to use and solve our problems. So that's my understanding. It may not. It is not that you cannot do it. You may be able to do it.
Yeah, maybe that with the open source software, you have to write much more coding actually compared to
Yeah.
the commercially
Yes.
available.
Yes. So you will have to do
For
more than that.
because you will get a platform and most of the thing, whatever you need, maybe at the high end part, you have to write your own code somewhere.
Yes.
Any questions from participants?
Hello,
Yes, sir. Good afternoon.
good afternoon. So I have one question actually.
You may know Dr. Jalesh, na? Dr. Gaurav. Jalesh also did PhD during our time also.
Yeah. 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 Yeah, I remember. Yeah, Dr. Jalesh, how are you?
I'm fine. So I have one question regarding this molecular simulation or molecular modeling. So in process control, we use a model and model-based control. We take feedback and then we take corrective action based on the control algorithm. So does this molecular simulation based model, can be used for closed loop control of your process?
Dr. Jalesh, this molecular simulation is more specific to materials, understanding materials and their properties. I understand what you're trying to say is more in the process control. You have those feedback and feed-forward controls.
Yeah.
But they are more process oriented, and there's no concept of materials optimization which is involved. These softwares, as of now, the one which I said, Material Studio, is till now they have not been able to connect it to process. But yes, now there is a connection that they are trying to do with the process part. But definitely understanding and evaluating different process control strategies. As of now, this software is not engaged with that. It may not help you.
Yeah, so sometimes some properties you might be monitoring during the synthesis of composites.
Yes, yes. So
And if the property is not as per the design value, then you need to take some corrective action,
yeah.
right?
So
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 online, while the process of synthesizing composites, if something goes wrong, then you may be able to take some corrective action using the control algorithms. Maybe I don't know.
yeah. No, in terms of synthesis part, it definitely supports synthesis because, for instance, you may have, uh, let's say, five molecules or five components into your composite that you're planning. It could be impact modifier. It could be a blend compatibilizer. It could be two blend polymers. So you may have four to five molecules into the system. But what will be the best combination of these molecules? If you tend to design a DOE and you actually run all those data points and then find out the properties, then it might be really difficult and troubling at your end in terms of both time as well as resources. So molecular simulations will help, at least in the preliminary level, to give you an idea where you should be heading, what component should be taken at what compositions and stuff like that. So it will probably make your job much more easier in final decision of what could be the range of the components that you're planning to use.
Okay, okay. Good, thank you.
So any other question from participant side before we end this session? So I would like to thank Dr. Gaurav Manik again to accept our invitations and to actually, because this is a new technique not very commonly used, just like other computational techniques. So this is a higher end techniques, and yeah, it's easy, not easy actually. It's actually good to design anything at the molecular the level actually, and with some specific properties, and just like the synthesis of new molecules, maybe new solvents, new coatings, or any the designing of new product, I think can be done by this molecular simulation only. So, sir, thank you very much for accepting and be the part and giving a wonderful informations and with a lot of details. So I would definitely start it soon actually. So I may take the help from you also.
Sure, sure.
So with this, thank you very much, and we will start our next session is after 5 minutes. Actually, we can take a 5 minute break for that.
Thank you,
So
Dr.
our
Raj.
next session would be by Professor Dajalish on solution of nonlinear algebraic equations, ODEs and PDEs actually. So we will talk on that thing. So thank you very much, sir, once again.
Thank you. Thank you. Thank you. Thank you. Bye. Take care.